In this lecture we are going to continue from where we left in the previous lecture. We are doing the planar elasticity problem, and for that problem we had derived the weak formulation, and we had said that the weak formulation, let us put everything in perspective again. Weak formulation corresponds to what? If I have a mesh, I make a very simple mesh here. Okay, let traction be specified on this edge. Okay, this is traction vector T is equal to Tx into I plus 0, because it's the x traction. I could have displacement here fixed to 0, that is u here is equal to 0. Okay, and let's say in a very simplistic situation I am using linear elements to solve this problem, that is piecewise linear approximation is used to solve this problem. Then these would be the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, and we had said, just like we had done in the 1D problem or in the single variable problem, I will have the basis function defined as this, that phi I is such that it is 1 at a node, well, and it falls off to 0 at the neighboring nodes. Okay, so this for example is my phi 5. Okay, so with this understanding we had said that then we are going to define our finite element solution UFE is U1 FE, and the components of it are U1 FE and U2 FE, and they are given by sigma I is equal to 1 to n. I may have n nodes in the domain, n is equal to 9 in this case, and the way we had defined them is alpha 2i minus 1 phi I was U1 FE, and U2 FE was some alpha 2i phi I, where we said that corresponding to every node there are so called 2 degrees of freedom, that is the alpha 1, 3, 5, 7, 9 and so on, they correspond to U1 FE, alpha 2, 4, 6, 8 and so on, they correspond to U2 FE. Okay, so here for example n is equal to 9, here n is equal to 9, the total number of nodes, and here I will have the degrees of freedom 1 and 2, 3 and 4, 5 and 6, 7 and 8, 9 and 10, 11 and 12, 13 and 14, 15 and 16, and 17 and 18. So the total number of unknowns becomes twice the number of nodes, which is 2n, because we are talking of a problem which has 2 unknown functions. Okay, so here it is 2n number of unknowns. Okay, so our job was to try to set up the 2n equations that we have to solve in order to get these 2n coefficients alpha I. This is of size 2n. Okay, so this is what we had started off with, and we said that in order to construct this equation we will go and look at the equation corresponding to phi 5, okay, or phi I in the general case. And we said, how did we do it? We chose the W, that is the test function, in a weak formulation. Our weak formulation was integral over the area sigma xx due to the finite element solution into, this is due to UFE, okay, into Exx due to the test function W plus sigma yy due to UFE into Eyy due to w plus tau xy due to the finite element solution into gamma xy due to the w, whole thing integrated over the area is equal to integral over the area of f1 w1 plus f2 w2, okay, dA plus on the Neumann boundary gamma n T1 W1 plus T2 W2 ds. So this we had done. What we said is we are going to choose W of two types. So corresponding to phi I, okay, I is equal to 1 to n, choose the vector W. I could write it like this: vector W is equal to phi I 0, okay, and we claimed that this W satisfies all the geometric constraints that are required by the W to be satisfied, okay. That is, I am taking the W2 component to be 0, W1 component to be phi I, and then put this in the weak form that we have obtained to get the equation which we had stopped at as the 2i minus 1th equation, okay. Then we said this was first choice. Choice B was choose W equal to 0 phi I, and this, when I put this is also an admissible W. When I put this in the weak formulation, I will get the 2ith equation. And you see that this way we construct all the 2n equations which are required in order to solve the problem, okay. And what were our 2i equations? We got that 2i minus 1 equation was given by the strain due to the choice of W that we have taken is equal to phi I minus x. Eyy will be equal to, because here I have taken W2 to be 0, 0, and sorry, not E, I am using gamma, so I will use gamma xy due to this W is going to be equal to phi I comma y, that is del W1 del y, okay. This is my state of strain. I put it in my weak form, so I will get integral over area sigma xx due to the finite element solution into the strain due to this, which is phi I comma x, plus sigma yy into the strain due to this displacement, which is 0, okay, plus tau xy into the strain due to this W, which is phi I comma y dA. This is equal to integral over area of f1 into phi I dA, okay. F2 will do no work because we have taken W to be 0, plus integral over the boundary, I will have T1 phi I ds. This is my equation A, let me call it. So this is my first equation. Now we said that 2i minus 1th equation is set, okay, where here the sigma xx and so on, they will come out of the representation of UFE, okay. So let's now go and talk of the 2ith equation. I'll get integral over the area So for the 2ith equation, what do I have? Exx is equal to 0, because we have taken w is equal to 0 phi I. Eyy is equal to phi I comma y, and gamma xy will be quite easy to see, phi I comma x. So this will give me, when I put this in the weak form, I will get sigma xx into exx, which is 0, plus sigma yy into eyy due to w, which is phi I comma y, plus tau xy into the gamma xy due to this choice of w, which is phi I comma x. This dA is equal to integral over the area of f2 phi I dA plus integral over gamma n t2 phi I ds. So this is going to be the 2ith equation. Let me call it by B. Okay. Now if I write A and B together, okay, what will I get? If I write A and B together, that is the equations, the 2 equations corresponding to the phi I, then I will get, if you see, I can write it like this: integral over the area. The first equation will be given by, let me do it like this. So the first equation, I will have something here into the stress vector sigma, I can write it like this. Okay, this is equal to, I will have here as integral over the area f1 phi I, f2 phi I dA plus integral over gamma n, I will have t1 phi I, t2 phi I dA. Okay, now let us look at the first equation. So sigma xx into what will I have? I will have sigma xx into phi I comma x, phi I comma x, sigma yy into 0, sigma xy into phi I comma y. Okay. Similarly, as far as this one is concerned, for the second equation, I will have 0 into sigma xx, phi I comma y, and phi I comma x. Okay. So this is the 2 equations I have written in kind of a matrix form. Okay. Now if I write all these equations corresponding to the various i's, and what do I have for sigma here? Sigma, if I go back to what I had done in the previous lecture, it was given as CB alpha. Alpha was the vector of the unknown coefficients, that is 2n unknown coefficients. So this is what I will get. Now I start writing one below the other these equations corresponding to I equal to 1, 2, 3, 4, 5, 6. What will I see? That here I will have phi 1 comma x, phi 1 comma y, phi 1 comma y, phi 1 comma x, then I will have phi 2 comma x, and so on, one below the other if I write. Okay. This, if I do the whole job all the way down to the 2n equations, this will be nothing but B transpose. This is exactly B transpose. One can work it out, it's very easy. The algebra is only tedious. Okay. So what I get, that I will end up getting integral over the element, over the domain B transpose CB dA, this is a matrix into the vector alpha is equal to, okay, here is the vector f. What is f? That's very easy. The first entry of f2i minus 1 will be f1 integral phi I, f plus integral of t1 phi I, and f2i will be integral over the area of f2 phi I plus integral over the Neumann boundary of t2 phi I. Okay, so this is the generic representation that we are going to get if we write the whole equation together. What is this then? This is now the global matrix K, which is the size 2n by 2n. Okay, this is into alpha 2n, and this is f, which is of size 2n. Okay, so the global stiffness matrix comes out of the integral over the area of what we call as the BTDB matrix. D is generally used as the material matrix instead of the C that we have used here. Okay, that's just a convention, naming convention. So I could do these things, this integral, and then I'm done. That is, I have my global stiffness matrix. Now it should be relatively easy to convert this to the element pieces which could be assembled back to get the global equations. Okay, so what can I do? I can write now this as integral over elements 1 to, I'll call it as number of elements into the over the area of the element L, okay, of this piece. So this will be this guy. Similarly, f I can write as summation over the elements, okay, of f due to the element L. Okay, now it's just a matter of obtaining these integrals. Now obviously, in order to obtain these integrals, what do? We convert it to the element notation. That is, we write everything in terms of the element shape functions instead of the global basis functions, because we are looking at the restriction of the basis functions to the element. Okay, so we'll do that. Similarly, the load vector will also be written in terms of the element shape functions. The integrals will be done as we have done till now for the 1D and the single variable problem in 2D. Integrals will be converted to an integral over the master element, because that's where we can do the numerical integration, okay, and then evaluate it on the computer. So as far as numerical integration and those aspects are concerned, we are not going to get into that now, because that part we have done enough of it. So let us now go and look at the element calculation. So how will I do this? So in order to do this, let's go back to our original figure. So let's say that this is element, we'll give some names to these elements. Let me give, this is element 1, this is element 2, this is element 3, 4, 5, 6, 7 and 8. So these are our 8 elements that we have taken for this simple problem that we are considering here. Okay, so now for these elements, so the number of elements in this case for the example problem is 4. Okay, so now let's go and do the following. That is, I have a generic element, some generic element. Okay, I will do it with the piecewise linears only. The job can be extended to the higher order ones. Okay, where these are the global nodes I, J, K. This is the generic element L. Okay, So this is the global node I, J, K. Similarly, if you are talking of the higher order elements, approximations, then we'll have the global interior nodes also, the mid-side nodes and the volume nodes and the area nodes, which depends on the order of approximation. So these are the global nodes I, J, K. So what do we do when we go to the element convention? Then this I will correspond to 1, this J will correspond to 2, this will correspond to. So in the element, I am giving a new naming convention. This is my node 1, 2 and 3. Okay. So here I had, corresponding to this node, I had phi I globally. In the element, I'll call it N1 of the element. Here I had phi j globally. Here I'll call it as N2 of element L. And here I had phi k globally, which is the same as N3 of the element L. Okay. So what would the finite element solution in the element look like? So UFE, the vector UFE in the element L would be given by sum I is equal to 1 to 3 in this case. Okay. Alpha I of the element L, N I of the element, sorry, it won't be alpha I, it will be alpha, we will have to do the appropriate thing, alpha 2I minus 1 of the element L. Okay. Similarly, the second component of the displacement, or the V component, will be alpha 2I of the element L, Ni of the element L. Okay. Now this alpha 2I and alpha I, alpha 2I, they correspond to what? So here, corresponding to this guy, I will have the global degrees of freedom would have been alpha 2 big I minus 1 and alpha 2 big I. Here it will be alpha big 2j minus 1 and alpha big 2j, and here it will be alpha 2k minus 1 and alpha 2k. So as far as we are concerned, these will become, this will correspond to alpha 1 of the element L, this will correspond to alpha 2 of the element L, this will correspond to alpha 3 of the element L, alpha 4 and alpha 5 of the element L and alpha 6 of the element L. Again, if you see, we have done a counterclockwise enumeration of the degrees of freedom. That is, we went from here to here to here and not from here to here to here. Okay, this is our choice. It's not that I have to make this node 1, I could have made this one 1, but it's the naming convention that we choose at the element level. The bottom line is it should be counterclockwise. Okay, the node should be numbered in a counterclockwise manner. Okay, so once we have this, so we know this local to global enumeration, we'll have to establish this. How will we establish this? This is when we do the degrees of freedom creation and numbering. That's where we go and establish this relationship. Okay, or it's called the connectivity matrix, connectivity information. Okay, this has to be created at that time. Okay, and this is not difficult to create for the mesh. Okay, so once I have this, so what it tells us that the finite element solution in the element is given in terms of these guys. So now the life is a little bit easy. When we talk of the B in the element, the matrix B that we have created, the B will have in the element non-zero entries only corresponding to the basis functions which are non-zero in the element. That is the phi I, the phi big I, phi big J and phi big K. Corresponding to those only, the B will have a non-zero entry for the element. All other phi's will have 0 entry. So we will write, but now we are writing these in terms of the N1, N2, N3 of the element. So we can write the B transpose CB matrix at the element level and understand where to put them in the global matrix. That will do the job. So, what is the B matrix at the element level? So, the B matrix at the element level for this case, remember that I am taking as an example a piecewise linear problem, will be, if I do it, n1 of the element comma x, okay, 0, n2 of the element comma x, 0, n3 of the element comma x, 0. Similarly, I will have 0, n1 comma y for the element, 0, n2 of the element comma y, 0, n3 of the element comma y. And here I will have n1 of the element comma y, n1 of the element comma x, n2 of the element comma y, n2 of the element comma x, n3 of the element comma y, and n3 of the element comma x. This is B, I will call it for the element L. Okay. So this is now, in the case of the linear approximation, it is 3 by 6, right, because there are 3 basis functions. By the same token, if we have elements of order P, then I will essentially have how many unknowns in the element? I will have, if you see, P plus 1 into P plus 2 divided by 2 number of degrees of freedom, number of nodes, into the number of degrees of freedom per node. That is, it will be P plus 1 into P plus 2. So this quantity would be P plus 1 into P plus 2. If you see for the linear, we had P plus 1 is 2, this one is 3, so 2 into 3, 6. Okay, so this is going to be the BL matrix that we have created at the element level. Similarly, now it's rather easy to define the element stiffness matrix, that is the part of B transpose CA that is going to come out of the element, okay, is integral BL transpose CBL dA. Okay, what will happen to the load vector? The load vector will be so for we have for I is equal to 1 to P plus 1 into P plus 2 divided by 2. Okay, I will have F from the element to I minus 1, that is, it corresponds to the choice W is equal to phi I, phi big I, 0. Okay, this will be equal to integral over the area of the element, it will be integral over the area of the element, F1 in the element into N1 in the element, Ni in the element. Let me erase this and redo it. Okay, Ni in the element dA plus, if the element shares an edge with the Neumann boundary, that is, let this element have an edge which sits on the Neumann boundary. Okay, so it could be, this is my node 1 of the element, node 2, node 3, this is going to be my edge 1, this is edge 2, this is edge 3. So this edge is common with the Neumann boundary, so we will say that denote the boundary of the element as gamma L intersection the Neumann boundary of the domain, okay, T1 NIL ds. Similarly, f2i of the element will be integral over al f2 ni of the element dA plus integral over gamma L intersection with gamma n T2 ni L ds. So this is going to give us the load vector for the element. Note something very carefully, that this is an integral over the area. This f1 ni L dA is an integral over the area of the element. Area of the element is this. So for that we'll have to use the integration points defined over the area of the element. While this quantity and this quantity, these are defined, these are integrals obtained over the edge of the element. Edge is a line. So this is a one-dimensional integration. So in order to do this integration, we have to transform this edge to the -1 to +1 edge, okay, and then do the integral over there. Okay, transformation we should be able to do it very easily. That is, take this edge to this edge, get the integration points, because this is where I know the integration points, and do the integration by summation there. Okay, so this has to be done as a separate loop in each element over the three edges of the element, and you have to carry the information about which edge of the element lies on the domain boundary and which does not. For an edge which does not lie on the domain boundary, like here these internal edges, I do not do anything. For an edge which lies on a domain boundary with zero displacement or zero traction conditions, I don't do anything, because those integrals on the right hand side become 0. Only for the case where the traction conditions given, the traction boundary conditions, are non-zero, in those cases I have to do these integrals on the boundary and put them in the load term. Okay, so here we are doing things concurrently. The boundary condition, the normal boundary condition, is taken care of simultaneously with the load calculation. In the 1D case, we went and very easily handled the two endpoints separately. Here we don't, because we don't have that luxury. Okay, we do it right away. So again, if I go back here, if I look at these elements, you see for element 1, I do nothing on any of these three edges, because on these three edges either zero traction condition is given or no boundary condition, or these are an internal edges. If I go to element 2, here the displacement is 0 on the third edge of the element 2, on this edge of the element 2. So as far as this element is concerned, again I do nothing as far as the integrals on the boundary is concerned. In element 3, I come to the second edge. Let this be edge 1 for the element 3. Here I have to do these integrals on the boundary, while on the other two edges I do nothing. Similarly, for element 7, I have to do the integral on this edge, do nothing here, and for all the other elements I do nothing. Finally, I am going to go and enforce the displacement boundary conditions explicitly, just like we did earlier. That is, we have to force in this problem alpha 1 alpha 2 equal to 0, because the vector u is 0 on this edge. Similarly, I have to force alpha 7 alpha 8 equal to 0 and alpha 13 alpha 14 equal to 0. Okay, so this way I can construct let me come back to what we were doing, construct the element load vector entries and the element stiffness entries. Okay, once we have done this, then we go back to our this connectivity information and simply assemble the entries of the element stiffness matrix and the load vector in the corresponding entries in the global stiffness matrix and the global load vectors. Okay, here we will be doing things two at a time, because corresponding to each phi I there are two unknown coefficients, alpha 2i minus 1 and alpha 2i. Okay, So this is how one would go ahead and do the element calculations, assemble and set up the problem to be solved. Okay. Now this is nice. Can't we do this in a more explicit way? This B transpose CB approach is something that is commonly available in all the books, and this is what people follow. But here something which I don't like personally is that here we are dealing with matrices. We have to store these matrices for every integration point, because this integral will be written in terms of summation over integration points. So at each integration point I have to go and compute the values of the shape functions and the derivatives, construct this matrix BL and do BL transpose CB at each integration point, then put it in. Can't I do this explicitly? Because that will reduce the cost of computation, because if we can do this job explicitly, it is quite easy. So if I go back to my element equation, I look at the 2i minus 1 equation. Okay. If I look at that equation, I will have integral over the area sigma xx n, I am dropping the L, n I comma x plus tau xy n I comma y dA. This is going to be the row corresponding to n 2i to alpha 2i minus 1 in the element, okay, or corresponding to ni in the element. Now what about this? Sigma xx is actually, by what we have done, C11 exx plus C12 eyy, okay. Tau xy is equal to C66 gamma xy, okay. Now I know that UFE in the element is given by the representation we have done already. So this is going to be equal to sigma I is equal to 1 to the number of unknowns in the element, okay. So here we have taken 3, okay, alpha 2i minus 1 in the element, okay, ni comma x. Similarly, this one will be sigma I is equal to 1 to 3 alpha 2i in the element n I comma y, right. And similarly this one will be sigma I is equal to 1 to 3 alpha 2i minus 1 in the element n I comma y plus sigma I is equal to 1 to 3 alpha 2i in the element n I comma x, okay. So what am I trying to get at? So corresponding to the choice W is equal to ni of the element 0, okay, I can explicitly get the stiffness entries in terms of the derivatives of the ni's and the nj's, okay. So how will I do it? So corresponding to I 2i minus 1, so for row 2i minus 1, okay, what will I do? Take columns, column will go from 1 to 6 in this case, or in the general case 1 to p plus 1 into p plus 2, okay. So let's now look at the column 2j minus 1. So for the row 2i minus 1, the column 2j minus 1 will have contributions due to, you see, the alpha 2i minus 1. So it will be this one and it will be this one. Okay, so I will get this as essentially C11 n j comma x into n I comma x plus C66 n j comma y into, if I go back here, I will have n I comma y, okay, into n I comma y. You integrate this quantity over the area. This will give me the column 2j minus 1. Similarly, remember for the row 2i minus 1, so column 2j will be the remaining part. It will be integral over the area of C12 n j comma y and I comma x plus C66 and j comma x into ni comma y. Okay, where did this come from? I got this one from this part and this part. Okay, so very easily I can get these entries explicitly. I put it in the loop for the integration, loop over the integration points, and compute these quantities. Similarly, for the row 2i, if you take the row 2i for the element, okay, this will correspond to integral over the area, okay, sigma xx will be, part will be 0, sigma yy, okay, n I comma y plus tau xy n I comma x dA. Okay. Now this part again I can write in terms of the 2j minus 1th column and the 2jth column. So column here, if I do column 2j minus 1, okay, so this will have integral over the area of C. If I go back to the material matrix for sigma yy, it is C12 into Exx. So C12 n j comma x n I comma y, okay, plus C66 n j comma y n I comma x integrated over the area. Similarly, column 2j, this would mean I will do integral over the area of C22 n j comma y n I comma y plus C66 n j comma x n I comma x. Okay, so it's very easy to write these expressions, and this is in some way what is it doing is this explicit operation of doing this B transpose dB has been written in terms of the expanded expressions that you would have obtained. Okay, one can check it that this is exactly what you will get out of the B transpose dB, and we can write it in a loop over the integration points and get the job done. So this will give me my element stiffness matrix. Similarly, the load vector entries that we can then handle, okay, and do the assembly to get the global system. Then in the global system I go and explicitly impose these boundary conditions for alpha 1, alpha 2, alpha 7, alpha 8 and so on, and solve the system to get the solution. Okay. One or two important issues that we should also look at. Let's take for example a boundary which is like this. Okay. And let's say, again I'm doing it with very simple mesh. Okay. Let's say that this is node 1, node 2, node 3, node 4, node 5. I'm solving it with piecewise linear approximation. You could do the same thing with the higher order ones. But here on this boundary, let's say traction conditions are given like this. T is equal to Tn into the normal in the n direction. What is the normal? Normal in this n direction. Okay, this is the normal vector. Okay, so the unit vector in the normal direction. If I am given the end load like this, how do I handle it? Okay, in this case, it's again very easy. We know that our traction vector, what we had written is as T is equal to T1 E1, where this is my x and y direction, or this is my 1 and 2 direction, plus T2 E2. This is also equivalent to writing it as Tn En plus Tt Et. Okay, and now how is Tn given? This is angle alpha. So En will be obtained quite easily. That's not a problem. The components of En, so it will be cos alpha I and cos sin alpha j. Okay, in terms of that. So I can write it like this. So the work done when we do the work on gamma n, T dotted with W ds could be also written as integral over gamma n Tn Wn plus Tt Wt ds. Okay. Now the question is that our approximation or the finite element solution is defined in terms of the Cartesian components, the xy components. So here, how do I write these in terms of the converted to the n and the t components? Okay, so it's very easy that Wn, we have Wn Wt is equal to, so here I have, essentially I want components in this coordinate system when I have components in this coordinate system. Okay, so if I look at Wn and Wt, so this is alpha, so Wn will be W1 cos alpha okay, plus W2 sin alpha, so it will be cos alpha sin alpha. Wt will be equal to minus W1 sin alpha plus W2 cos alpha. So this is W1, this is W2. So it's minus W1 sin alpha, W2 cos alpha. This in terms of W1 and W2. Remember, I am talking about the function defined on this face, the face which is this inclined face. Okay, so now it's very easy that I put the boundary condition, because here, for example, my t is 0, so let's knock this off. Wn will now be given as W1 cos alpha plus W2 sin alpha. Okay, and we have defined our W in terms of the Cartesian coordinates, that is in terms of W1, the components W1 and W2. So what will happen to the nodal equations, that I will write essentially Tn into W into cos alpha integrated against the phi corresponding to this one will give me the first load term. Okay, let me do it. Let's say corresponding to node phi, the node 3, what will I get as my load contribution corresponding to phi 3? So it will be integral over this edge, okay, Tn into cos alpha, okay, phi 3. This will go into equation F5, right? It will go to the x component of the load vector. Similarly, the other one will have Tn sin alpha phi 3, which will go to F6. Okay. If I go to the next one, here I will have Tn cos alpha phi 5 integral will go to F9 corresponding to 2i minus 1 here, and Tn sin alpha phi 5 will go to F10. Okay. So this way we can handle a inclined boundary. What about an inclined displacement condition on an inclined edge? For example, if I have this edge and instead of this I have displacements given here, let's say rollers, that the normal displacement is 0. Okay, that condition, that constraint has to be imposed. So what does this mean? That this will mean in this case that un is 0. Now un is given as a combination of u1 and u2 as u1 cos alpha plus u2 sin alpha. That has to be 0 on this edge. So we do everything that we do in the standard way, assemble the global stiffness matrix and the load vector, and then go and impose this condition to eliminate one of the unknown coefficients. That is, I can write here on this edge the un as equal to what? Alpha 5 phi 5 into cosine alpha plus alpha 9 phi 5 alpha 5 phi 3 cosine alpha plus alpha 9 phi 5 cosine alpha plus alpha 6 phi 3 sin alpha plus alpha 10 phi 5 sin alpha is equal to 0. Okay, and from there I can write these alphas, that is alpha 5 cosine alpha plus alpha 6 sin alpha is equal to 0, and from here I will get alpha 9 sin alpha cosine alpha cos alpha plus alpha 10 sin alpha is equal to 0. So this constraint has to be imposed on the stiffness matrix. I can eliminate one of them in terms of the other, and then the equations also get properly modified, and I will solve that system to get the solution to the problem. Okay. So with this I would like to conclude the part on the element calculation, the construction of the global stiffness and the load vectors for the planar elasticity problem. Okay, and you see that everything follows the same line of attack that we had started in the first lecture. Okay, what we'll talk next in the next lecture is how to post process the stresses that you get out of the finite element solution, because we know that those stresses by construction, especially for lower p orders, are essentially discontinuous, while the state of stress in my actual case is continuous. Okay, so I'll have to do some post processing just like we did in the one dimensional problem, okay, in order to obtain a better, seemingly better, or hopefully a better state of stress out of the finite element data. And then we'll go and look at some curved geometries, how do you handle curved domains? Here we have not handled curved domains. In that case, what kind of an approximation for the geometry has to be done, and how does it affect the scheme of things that we have?